Hello students, in this video we'll discuss several common continuous random variables, their PDFs and their CDFs. So we'll first consider let x be a random variable with PDF f of x. And what this PDF will be is this PDF will be 0 if x is not in the interval a to b, and it will be equal to 1 over b minus a if x is in the interval a to b. So we call this random variable, then x is a uniform random variable and we write that x is uniform on the interval a to b. Now we can clearly see that this is a PDF. Indeed, if I integrate this from a to b, that's the only part of the range, the domain of the function f, where they're non-zero. I'll do 1 over b minus a dx. So this will just be 1 over b minus a times b minus a, which is equal to 1. And so indeed, this is a valid PDF. So let's find the CDF. So the CDF of a uniform on AB random variable. Well, how do we do that? We want the probability that x is less than or equal to x. And so let's visualize this graphically. What we have over here is here's a, and then here's b, and then here's the 1 over b minus a height. So there's my PDF, looks like this. Now if we pick a value of x over, so there are 3 ranges to consider. There's this first range over here where you're less than a. There's this second range over here where you're between a and b. And there's this third range over here where you're bigger than b. And so let's see what happens. If x is in this first range, so if x is in range I, so if x is in the first range, range I, then the PDF is equal to 0. So let's fill this in. So you're 0 over here. And you jump up, then you jump down, and you're 0 over here. So if you're in that first range, the PDF is 0. So what we have over here is we'll have that implies that f of x will just be 0. If x is in the second range, say that you're over here, that's x, then we will integrate just that little small chunk over there, that little rectangle, and then we'll see that the area of that rectangle is the height is going to be 1 over b minus a, and the width is going to be x minus a. So then f of x in this range will be x minus a over b minus a. And finally, if you're in the third range, then you've integrated all of the mass of the PDF. So if you're in the third range, then f of x is just equal to 1. So if we put this together, what we can see is we can see f of x is 0 if x is less than a. It is x minus a over b minus a if x is between a and b. And it's equal to 1 if x is larger than b. And so this is our CDF for a uniform random variable. We can also consider another random variable. Let's consider this random variable. Let's let f of x be 1 over theta e to the negative x over theta. We can check to see that this is indeed a random variable. So this is if x is greater than or equal to 0. And what will be is that if we specify that x is greater than or equal to 0 with no other conditions, it's assumed that the PDF is 0 in the other range. So the PDF will be equal to 0 if x is negative. So what these random variables are, so this corresponds to random variable x, which is exponential with parameter theta. And so if we want to find the CDF of this random variable, so the CDF of an exponential random variable with parameter theta, will be f of x. And that will be the integral from 0 to x, because if you're before 0, if x is, so we'll note that f of x is equal to 0 if x is less than 0, because the PDF is also 0 there. But if x is positive, then we'll go from 0 to x, and then we'll have 1 over theta e to the negative t over theta dt. And we should note that we've changed the x in our integrals for the PDF to t's, because x is now being used as the variable of integration. So now what we can see here is I claim this is negative e to the negative t over theta, because if we do the derivative of this, I'll get a positive 1 over theta, negative t over theta. So this is the antiderivative of this function over here, evaluated from t equals 0 to t equals x. And so what we see over here is the bottom limit is going to be positive. So we'll go into, and I plug in t equals 0 for the bottom limit, I'll get a negative negative, which turns into a positive 1. And when I plug in x over here on the top limit, I'll get negative e to the negative x over theta for x greater than 0. So this over here, 1 minus e to the negative x over theta, is the cumulative distribution function of an exponential random variable whose parameter is theta. In future videos, we'll see how to compute the mean and variance of these random variables in terms of their parameters. Thank you very much.